so nanotechnology, I think, would be everything that is connected to semiconductors or like communication and computation technologies and stuff like that. And that clearly plays a big role both in the academic research as well as in particular in the industrial research. I think a good part of the focused ion beams end up in the semiconductor industry and everything that is broadly related to it. Nanomaterials, I think that's more academic, if I'm right. And there, the focused ion beams, well, play two roles. One of them is traditionally in the analysis, like, you do gallium-based or xenon-based TEM prep or atom probe tomography samples that are made with the focused ion beams. But then this is something that we tried to show in Fit for Nano is that you can actually create nanostructured materials very nicely with a focused ion beam in a spatial resolved manner by going away from gallium. I mean, also with gallium, but going to other ions gives you a lot of freedom there, and you can tune the material properties on the nanoscale and create new functionality.
It's really interplay between ion types, energies, charge state, and the material.
This is a good question. So fortunately, focused ion beam processing is conceptually simple. And so there's no rocket science involved. And usually people, once they started with focused ion beams or focused electron beams, they like it so much that they never stop it during their life. And I think, so yes, for training, we could maybe start more effort in kind of establishing really dedicated training schools. But this is not maybe the core of the problem. I think the core of the problem is that many people are not aware of the capabilities of focused ion beams. And in a broad range of the communities, different communities, it's just known as a tool to prepare TEM lamellars. And I think this is what we have to do. So basically, before we can invest more in education, what we certainly should do is we should create awareness and become visible and basically show off with all the amazing things you can do and all the development that has already been done.
The other end of the spectrum would be then the helium ion microscope, which has probably the smallest spot size. It's just 3 atoms where you create the ions, but you only use the ion beam that comes from one of the atoms. So it's basically an atom where you ionize all the heliums, and then you are able to focus down that ion beam back to something larger than an atom, so less than a nanometer. And then you can do very fine and tiny cutting. You can prepare phononic structures where you just do a fine cut. And however, you also, it comes with less ion current, so usually you would not create the bigger structures with a helium ion microscope.
It's mostly that people would know what an electron microscope is and what you can do with it. But when it comes to helium ion microscopy, it's new to them, definitely. And in many cases, I found that giving those students a proper training enables them after not too long time to measure their samples themselves and so on. And they find that the helium ion microscope is not more complicated than a scanning electron microscope, which is a very good thing. And I think it's also a selling point for this tool.
In ideal life, of course, you always want to use the most accurate model, but you need infinite computational power for that, and also lots of time to wait before calculations are done. So in reality, you're always trying to find a compromise between accuracy and efficiency. And it's known that, well, in general, my policy, probably not my policy, it's, I would say most scientists would say that from simple to complicated.
Can be a disadvantage, but also for special applications, it can be a feature that people want to study the process that happens in a wall of a fusion reactor, and where you can simulate what will happen in a fusion reactor by just implanting the helium in your sample.
There will not be the Christmas tree focused ion beam system which solves all the problems. And I think that technological development will rather go towards a direction where specific focused ion beam systems are developed for specific applications. Because there are applications where you want to remove large chunks of material in a short time with low chemical interaction. And for these heavy noble gas ions, certainly, for example, provided with a plasma FIP that realizes large currents is one direction. And this is interesting also for life science applications. And then I expect, for example, focused ion beam systems, which provide cryo option and a full workflow for tomography. Tomography means that you slice a material, you take images, and then you reconstruct the whole beast in a three-dimensional volume again.
So it would be kind of customized systems, no? Which also are more complex. So we, in some cases, also incorporating laser, let's say, machining, or as you mentioned, no, cryo-enabled, let's say, facilities or capabilities, and also automation of routines, no? For instance,
as I said, there's a wish that I have, which is one would definitely need a cryo stage at some point, and also I would love to see a combination with the scanning electron microscope. But I think where the main potential is at the moment is definitely everything that is related to inorganic nanoparticles, because the high resolution of the helium ion beam is actually perfect for detecting nanoparticles in the weirdest matrices that one could think of. That could be a leaf of a tree that was sampling, basically passively sampling nanoparticles from the air. It can also be nanoparticles in soil and so on and so forth. And if then the helium ion microscope is combined with the SIMS, which is at the moment, it is already available. So if you combine it with that, then you have also the analytical capabilities to analyze the nanoparticles. And yeah, I would say this is definitely a field that should be explored much more in future.
It's very efficient.
Thank you very much.
If you start calculations using DFT molecular dynamics and in parallel train machine learning potential, and slowly but surely replace more and more calculations with DFT calculations with machine learning potentials. But once the code tells you that you are in the new configuration, for example, atom somehow kicked out, and this configuration is very high in energy, so that it never been, assessed before, then you immediately go back to DFT within the same code and calculate energy of this and add this to your training set. In fact, actually, the popular code WASP we're using now, it works exactly this way, and it really speeds up the calculations. So this is not pure machine learning potential calculations, it's DFT plus machine learning, but the more you run, the cheaper calculations.
So I think the in 5 or 10 years, I think it's not realistic that we come up with extremely new stuff, but I think we should be able to also use our FIP systems more efficiently, to do automatization and to utilize also more machine time, and do more fancy stuff with the tools that we already.
Depends on how you configure it.
Exactly.
So either by a dedicated gallium or xenon FIP with 2 micromanipulators for lift out and an SEM to observe the entire process, and then you do mass production of TEM samples or APT samples or whatever, or you go for something like, a liquid metal alloy source with a heater stage and an EDX or some other weird detector in there to be, creative and do new stuff. But the customers will be different.
Yeah.
One is from industry, the other one is more from academia. And of course, there's overlap. But
yeah. In any case, it's in terms of market, let's say, it's a mature technology. It will stay there, no, in the market. And then probably, let's say, it will be incorporating new things, no, as needed and as provided, no, by academia or both, let's say, industry, let's say, implementations. Good. So long life to the focused IMBM technology.
Yeah.